So taking this weighting vector, we can use that for computing the Euclidean distance. Yeah? But once again, this is now specific to a point, because depending on which kind of feature of which kind of weighting vector we use, we get different distance measures. Yeah? So if we use the weighting vector of p, that would give us a different distance between p and q than if we use the weighting vector of q. Yeah? Because the weighting vector of q could be could have different entries here. Yeah? Because the epsilon neighborhood around p and q could have different preferences. Yeah? So this distance here is specific to a point, but of course we can make it symmetric in order to assign or to use it in dbScan. We typically need a symmetric distance function or distance measure. So we can make it symmetric by just taking the maximum of the two. Yeah? So and that is the so-called preference weighted distance function used then by dbScan between 2 points, which is the maximum of the distance from p to q and the distance from q to p. Yeah? So the distance from p to q means that we take the weighting vector of p, and from q to p means that we take the weighting vector of q. And those two things can be different. So the distance is maybe a little bit different. Well, if the weighting vectors of p and q are the same, then are the distance. Then the distances are also the same. But if the weighting vectors of p and q are different, then those are different. And then we just take the maximum in order to get a symmetric distance measure. Yeah, and then we define the so-called epsilon neighborhood of a point using this distance preference. The intuition is that instead of using an epsilon neighborhood in the entire space, we use an epsilon neighborhood which looks like an ellipsoid. So the features that have a small variance are actually weighted by 1 divided by kappa, and the other one. So sorry, this one here. Yeah. So this is somehow squeezed or bumped by a factor of kappa, and this one here, the direction of the high spread is not touched, so to say. Yeah. So that is how we actually get this 1 and this kappa into this weighting scheme here. Yeah. So the epsilon neighborhood now looks like a kind of ellipsoid, because we weight the ones that are relevant, like A1 here, with kappa, meaning that we need epsilon divided by kappa in order to get a distance of epsilon using this distance function here. Yeah? And the non-relevant attributes like A1 are weighted by 1, so in that case the extent of the epsilon neighborhood is epsilon. Yeah? So we get a kind of ellipsoid which is oriented along the directions or the features of small variance, actually. And that's what we probably want. Yeah? So that reflects our subspace preferences of each point. Now, since we have that, well, preference weighted core points, rect density reachability, connectivity, and so on, they are all based on preference neighborhoods. We can all define them as dbScan defines them, but the only difference is that we use these preference epsilon neighborhoods of points instead of the normal epsilon neighborhoods like those here. Yeah, so that is the only difference. So mathematically we can do everything again like dbScan does it, but just using this preference weighted neighborhoods. Yeah? And then a subspace preference cluster is just a maximum density connected set of points associated with a certain subspace preference vector, which is again the same as dbScan, but the only difference is that we have these preference vectors for each point and also for the neighborhoods and stuff like that. Yeah? And the result is that clusters now may again have arbitrary shape and size, of course, also in the subspace projection. So if you think about that, it's a kind of still a kind of sphere that we are spheres that we examine in the projection of the relevant features. Yeah, so also again in the direction of the irrelevant features, but the most important part is that we look for very, very small spheres that are dense enough in the subspace projection of the relevant features here. Yeah? So that is the basic idea of predicon here. Yeah, and then I just wanted to show you that there are some variants take it a little bit different. So DOC is, for example, one variant that is based on sampling. Yeah, so it computes clusters as dense hyperrectangles. Looks a little bit like Clique, the very first of subspace clustering. Yeah, same cluster model actually, but in another way, like Clique, it computes, or different to Clique actually, it computes these dense hyperrectangles from random sampling. Yeah? And it actually computes one cluster in each run, at most actually one cluster in each run, because each run is associated with some random sampling strategies, and it may happen that we don't sample the right points so that we don't find any dense hyperrectangles. Yeah? So in each run of DOC, we compute at most one clustering, or one cluster, not one clustering, one cluster. And for finding those hyperrectangles, and especially the subspaces, the relevant features of the hyperrectangles, this method uses random sampling. Yeah, and then I just want to mention there are a couple, or a plethora actually, of different further methods. So just to mention one here is the so-called COSA method, which learns a distance matrix that can also be used for clustering, but again, it learns that instance-based, on an instance-based locality assumption. That is pretty much the same as predicon and proclus. So it looks for local neighborhoods of, in that case, instances, so it's more like predicon, in the entire feature space, which is, as we already discussed, a kind of questionable assumption and a kind of probably severe limitation, because, well, if we take a look at this one here, then in that case, probably it's that is a good example where it probably goes right. But if we have a lot of noise points in here, which is very likely in high-dimensional spaces, so we don't see a clear subspace preference, even though we have a subspace cluster here in this projection, maybe, yeah. But in the high-dimensional, in the full-dimensional space, we don't see that in the local neighborhood. So we can expect that there is no clear preference, subspace preference for points in the local neighborhood of the points in the entire feature space. And then obviously the whole thing, like this one here, goes completely wrong. And the same holds true, of course, for this one here, where we again look for the locality. So also this procedure here is probably going wrong in that case. Yeah. Okay, so that was projected clustering, and next up we will look at something which is related to all that stuff here, but takes a completely different view on clustering and also on features, and they are called pattern-based clustering algorithms. Stay tuned.